The story of nuclear technology begins in the late 19th century. In 1896, Henry Becquerel discovered uranium salts emitted invisible rays that darkened photographic plates. Marie Curie dedicated her life to understanding radioactivity, discovering polonium and radium. Einstein's equation E=mx² revealed the incredible energy within the atom's nucleus. This discovery revolutionized physics and paved the way for harnessing nuclear energy. Scientists unlocked a powerful force, promising progress and posing threats. The discovery of nuclear fission in the late 1930s marked a turning point in the history of nuclear technology. Fission is the process of splitting an atom's nucleus, releasing tremendous energy. Scientists, led by Enrico Fermi, achieved the first self-sustaining nuclear chain reaction in 1942 at the University of Chicago. This breakthrough experiment, conducted under the stands of a football stadium, demonstrated the feasibility of controlled nuclear reactions. It opened up the possibility of harnessing nuclear energy for various applications, from generating electricity to creating powerful weapons. The Manhattan Project, a top-secret US government program during World War II, was launched to develop the atomic bomb. Scientists and engineers worked tirelessly, driven by the urgency of the war and the fear that Nazi Germany might develop the bomb first. The success of the Manhattan Project led to the creation of the first atomic bombs, forever changing the landscape of warfare and ushering in the nuclear age. This new era brought with it both unprecedented opportunities and grave dangers, forever altering the relationship between humanity and the atom. The destructive power of nuclear weapons was tragically demonstrated in August 1945, when the United States dropped atomic bombs on the Japanese cities of Hiroshima and Nagasaki. These bombings, which remain the only use of nuclear weapons in warfare, resulted in the deaths of hundreds of thousands of people and left a lasting legacy of devastation. The Hiroshima bomb, nicknamed Little Boy, exploded with the force of approximately 15,000 tons of TNT. The intense heat and blast wave obliterated everything within a 2-kilometer radius, instantly killing an estimated 80,000 people. 3 days later, the Fat Man bomb was dropped on Nagasaki, causing further death and destruction. The combined effects of the bombings, including radiation sickness and long-term health consequences, ultimately claimed over 200,000 lives. The bombings of Hiroshima and Nagasaki shocked the world and ushered in a new era of fear and uncertainty. The images of the devastated cities and the suffering of the survivors served as a stark reminder of the horrors of nuclear war. The aftermath of World War II saw the emergence of two superpowers, the United States and the Soviet Union, locked in a global rivalry known as the Cold War. Both nations possessed nuclear weapons, creating a climate of constant tension and fear. The Cold War arms race led to the development and stockpiling of increasingly powerful nuclear weapons. Each side sought to deter the other from attacking, believing that the threat of massive retaliation would prevent an all-out nuclear war. This strategy, known as mutually assured destruction, or MAD, created a precarious balance of terror. The world lived under the constant shadow of nuclear annihilation, with the possibility of accidental or intentional launches a constant source of anxiety. The Cold War era witnessed numerous close calls and near disasters, highlighting the fragility of this nuclear standoff. The Cuban Missile Crisis of 1962, when the United States and Soviet Union came perilously close to nuclear war, served as a stark reminder of the devastating consequences of miscalculation or escalation. Section 5. Atoms for peace, energy, medicine and more. While nuclear weapons cast a long shadow over the world, nuclear technology also offered tremendous potential for peaceful applications. Scientists and engineers explored ways to harness the power of the atom for the benefit of humanity. One of the most significant applications was nuclear power generation. Nuclear reactors using fission to produce heat could generate electricity on a large scale without emitting greenhouse gases. This promised a cleaner and more sustainable energy source compared to fossil fuels. Nuclear technology also revolutionized medicine. Radioactive isotopes, with their unique properties, became invaluable tools for diagnosis and treatment. They enabled doctors to image internal organs, track the movement of drugs within the body, and target and destroy cancerous tumors with precision. Agriculture also benefited from nuclear technology. Radioactive isotopes were used to develop new plant varieties, control pests, and preserve food. These advancements led to increased crop yields and enhanced food security for a growing global population. Section 6. The perils of the atom, Chernobyl and Fukushima. Despite its many benefits, nuclear technology also posed significant risks. Accidents at nuclear power plants and other facilities served as stark reminders of the potential for catastrophic consequences. The Chernobyl disaster in 1986 at a nuclear power plant in Ukraine stands as the worst nuclear accident in history. A flawed reactor design and human error led to a catastrophic explosion and fire, releasing massive amounts of radioactive material into the atmosphere. The Chernobyl accident resulted in widespread contamination, displacing thousands of people and causing long-term health problems. The disaster highlighted the importance of robust safety protocols and the need for international cooperation in managing nuclear risks. The Fukushima Daiichi nuclear disaster in 2011, triggered by a massive earthquake and tsunami in Japan, further underscored the vulnerability of nuclear power plants to natural disasters. The meltdown of 3 reactors at Fukushima led to the release of radioactive material, causing widespread environmental contamination. These accidents raised public concerns about the safety of nuclear power and prompted a reassessment of nuclear energy policies worldwide. Section 7. Nuclear waste. A legacy for future generations. One of the most challenging aspects of nuclear technology is the management of radioactive waste. The byproducts of nuclear fission remain radioactive for thousands of years, posing a long-term hazard to human health and the environment. Nuclear waste requires careful handling, storage, and disposal to prevent the release of radioactive material. Finding suitable long-term storage solutions for high-level radioactive waste remains a significant technical and political challenge. Deep geological repositories located in stable geological formations are considered the most viable option for isolating high-level waste from the biosphere for thousands of years. However, identifying and developing such repositories is a complex and costly endeavor. The legacy of nuclear waste is a reminder of the long-term responsibilities associated with nuclear technology. Ensuring the safe and ethical management of this waste is crucial for protecting future generations from its potential hazards. Section 8. Fusion power, a dream of clean energy. While fission has powered nuclear technology for decades, scientists dream of harnessing fusion, the process that powers the sun and stars. Fusion involves fusing light atomic nuclei to release energy, producing no long-lived radioactive waste and offering near-limitless clean energy. Fusion power has been a goal for decades, with researchers working to overcome immense technical challenges. Recent advancements in fusion technology have brought the dream of fusion power closer to reality. Despite challenges, fusion power represents a future of clean, safe, and abundant energy. The pursuit of fusion energy is a testament to human ingenuity. Section 9. The future of nuclear technology, a balancing act. The future of nuclear technology hangs in the balance. On one hand, nuclear power offers a low-carbon alternative to fossil fuels, and nuclear medicine continues to save lives. On the other hand, the risks of nuclear weapons proliferation and the challenges of nuclear waste disposal cannot be ignored. The international community faces the daunting task of finding ways to harness the benefits of nuclear technology while mitigating its risks. This requires strengthening non-proliferation efforts, improving the safety and security of nuclear facilities, and developing responsible solutions for nuclear waste management. Public perception of nuclear technology remains divided, shaped by historical events, cultural factors, and concerns about safety and waste disposal. Open and transparent communication about the risks and benefits of nuclear technology is crucial for fostering informed decision-making. Ultimately, the future of nuclear technology depends on our ability to balance its immense potential with the responsibility to use it wisely and safely. It is a challenge that demands international cooperation, technological innovation, and a shared commitment to safeguarding the well-being of both present and future generations.